you believe that human activity based on your belief in science is contributing to climate change?
The increase in the greenhouse gas concentrations in the atmosphere are having an effect. Our ability to predict that effect is very limited.
What are some model predictions in the past that have later turned out to be correct, like models from first principles predicting properties of climate that were only confirmed in subsequent observation?
Just the whole warming of the Earth that's occurred over the last few decades was a prediction of the climate models that has essentially come true.
This is the first three-dimensional model result that was done by Manabe and his colleagues at the Geophysical Fluid Dynamics Laboratory at Princeton.
I was a graduate student in the 1980s, and we had been looking at the warming trends and comparing that with model projections.
How can we predict what our future atmosphere will be like because of the greenhouse effect? This is one way, using a computer model of the atmosphere here at NASA Goddard.
We predicted 2 years ago that by 1990 you would see a warming of several tenths of a degree.
There was no doubt that fossil fuels were the main driver of higher CO2 emissions, and that CO2 emissions would lead to climate change, right? What Exxon was trying to figure out in the 70s and 80s was, when is it going to hit and how bad is it going to be? But they knew it was going to be bad. Like, they admitted it's going to be bad. They used the word catastrophic over and over again.
The actual temperature rise since my first major paper in 1981 has actually been faster than what we calculated then.
The model said, that sometime in the 1990s, the signal should start rising out of the noise.
November 1995, Madrid, the scientific community really got together and said, that's it. It's a complex problem, but we've seen the evidence and it all points in one direction.
And it's not just the global mean temperature. What's important is the spatial characteristic of it.
What happens in the upper atmosphere is, with more CO2, the atmosphere being so thin, it can just sort of radiate more effectively to space, and so the stratosphere cools.
The stratosphere has been cooling, at the same time the lower atmosphere has been warming.
So that's a prediction that the models make. That's exactly what happened.
And that pattern, that distinctive pattern, warming low down, cooling up high, is fundamentally inconsistent with natural causes.
So if it was something like heat coming out of the ocean or solar variability, you would expect the stratosphere and lower atmosphere to move together.
I didn't know whether global warming was real, whether it was completely bogus, or maybe it was twice as bad as people said. So my daughter and I, who at that time had a consulting firm, decided we would set up a nonprofit organization to study climate change ourselves. We brought in some really good people. Extraordinarily good people. I mean, at the level that Saul Perlmutter was a member of our team and a co-author of our papers when it was announced that he had won the Nobel Prize in Physics. So we had really good, Art Rosenfeld, who was a hero in energy conservation, but these were all people who shared the same doubts that I had. So we wound up doing an enormous effort, completely rebuilding a program to use historic temperature records, and did it in what we believe to be the best statistical approach to doing this. We managed to put together a record. We studied the systematics. I had no hope that we'd be able to address all the systematics. In the end, we could, and that came as a wonderful surprise to me. Each one required a great deal of effort. Poor station quality, the urban heat island effect, the data adjustment that's been done, and most important of all, the data selection bias, the fact that every other team was using less than 20% of the data, in some cases only about 7% of the data. So how did they pick their data? And did that lead to a bias, even an inadvertent bias? So we managed to address all these, and in the end we got a nice curve, a curve that showed the temperature, and it was rising. Now, we'd never expected to address the question of what caused it. I tried fitting it to an exponential. It actually wasn't a very good fit. Tried a parabola. No, it wasn't a good fit either. Okay, try the US population. No, it wasn't so good. Hey, dummy, try carbon dioxide. Smack on.
Yeah, it was, if I remember correctly, you got a correct fit when you also included carbon dioxide and, if I remember correctly, volcanoes?
Well, there were dips. And what we did to do the volcanoes is we did a one-parameter fit. That is, we included the dust record sulfate record actually, from the Arctic and Antarctic, the average sulfate record, and that's a series of dips. And then we added that in and adjusted one parameter to get a very good fit. We also added in solar variability. We tried this in many different ways. Tried just the straight sunspot record, running averages of the sunspot record, the IPCC function of solar intensity. We tried all of them. They didn't contribute. Now, we could rule this out in part, large part, because our record went back 260 years, whereas the IPCC record only went back really into the late 1800s. So we went back all the way to 1753, and we could do that by using our statistical methods. The uncertainties get large when you get back there, but it's still usable data, in particular because of the volcanoes, which are big excursions, volcanoes causing large negative temperature excursions. So I was flabbergasted. Not only was global warming real and roughly consistent with what the previous groups had said, but the match to carbon dioxide and the fact that solar variability was not responsible. We enabled us to rule out the primary alternative theory. Another alternative theory is that the absence of volcanic eruptions in the recent period is why it's warmer. But we could see these individual volcanic eruptions because we went back further in time. And we could see that their effects were temporary. So we could rule out the other one. In fact, we can rule out every scientific theory other than the greenhouse gas theory. Now, there are some people who say, oh, I believe it's something else. It's changes in the Earth's orbit. I wrote a book on the changes of the Earth's orbit, a technical book meant for graduate level study on the so-called Milankovitch cycles. It doesn't match those. Some people say, well, there's something else going on. And I say, what's the prediction you make? Oh, I don't know, it's random. Now, that's not what we call a scientific theory. If you say, well, it's something else and I don't know what it is, my answer is something else that just happens by accident to perfectly match the carbon dioxide increase. Are you serious?
The other thing that was predicted was that the high latitudes would warm more than the low latitudes, so the polar areas, especially in the north.
The temperatures will increase more so in the Arctic region, less so in the tropics.
The lower atmosphere sort of warms 2 to 3 degrees at most latitudes, but there's an amplification of the change in polar regions.
We know that the Arctic is being impacted much more dramatically than we are here in the mid-latitudes.
Some of this is due at least to this ice albedo feedback mechanism.
As the shiny white ice and snow melts and gets replaced by dark ocean and dark land surface that soaks up more of the sun's energy.
Models predict that lower latitudes warm up less than high latitudes. Well, did that happen? Yes.
Another projection was that the northern hemisphere should warm faster than the southern hemisphere because the land tends to be more on the north than in the south, and so the ocean acts as a big thermal heat sink, and so we would expect the southern hemisphere to warm more slowly than the north. That's exactly what's seen.
Models predict middle of continents warm up more than middle of oceans because of the heat capacities of the system. Did that happen? Yes.
We've done a bit of work looking at how the spread of climate models from the latest IPCC report compares to observations. Right now, at least, particularly with the current El Nino, observations are a little above the model mean. For the last decade or so, they've been a little below the model mean, but still well within the spread of climate models.
But other changes in our weather could be even more important than hotter summers.
Changes that could perhaps be starting already. The shifting of precipitation patterns from place to place, changes of the atmospheric winds, which mean that some people may actually start to see different storm patterns.
So in fact, early work with climate models had projected that there would be a shift in these storm tracks with the rain moving out over the ocean away from the land in parts of the southern hemisphere, and we are now actually seeing these changes take place.
Models predict night warms up more than day because of a variety of factors. Did that happen? Yes.
It has been over 50 years since climate scientists formally warned a U.S. president of the dangers of climate change. We have known that humans are affecting the climate of this planet since the late 1800s.
Science tells us that the climate is changing, and then human activity in some manner impacts that change. The ability to measure with precision the degree and extent of that impact and what to do about it are subject to continuing debate and dialogue.
Who can tell what the future will be like? NASA scientists have combined data from several climate models used by the UN Intergovernmental Panel on Climate Change to show how patterns of temperature and precipitation could change through the end of the 21st century. This visualization shows the expected changes in temperature and precipitation we might see, compared to the average levels of the late 20th century. The largest temperature increases are seen in the northern hemisphere. Across North America, areas that typically have snow, such as the Rocky Mountains and northern Canada, will see the earliest and largest temperature rise. The warming temperatures will eliminate the reflective and cooling effect of the white snow cover. This reduction in albedo is the reason why the Arctic region shows such dramatic warming, as the polar sea ice melts and the darker ocean water absorbs energy from the sun. In turn, the warmer water accelerates the melting of the sea ice. All around the globe, the land areas show a greater increase in temperature than the surrounding ocean waters. Evaporation of the water helps to keep the ocean surface cool, and the deep depths of the ocean have a large capacity to absorb energy before heating up. Off the coast of South America stretches an unusually warm patch of the Pacific Ocean. A cyclical occurrence, known as El Niño, causes more precipitation in that area of the Pacific and affects the climate throughout the region. And we can see that happen in this visualization of changes in precipitation. Models project warmer waters and increased precipitation to stretch across the Pacific Ocean to Indonesia as the century progresses. The monsoons over the Indian subcontinent will bring increased precipitation over a wider area, and Eastern Africa and the savannas of the Sahel could see precipitation increases up to 100%. At the same time, the Mediterranean will experience the opposite, a decrease over 40%. In general, the mid-latitude and subtropical dry regions are projected to see less precipitation, while the mid-latitude wet regions could see more precipitation. The poles and high latitudes are expected to also have increased precipitation. For North America, the models indicate more precipitation in the north and less in the south.